right? So you have in potentiometer, you have a battery of EMFE, and then you have connecting wires which have negligible resistance, and then you have a wire of 1 meter length, which is why it's also called potentiometer. You have a wire of 1 meter length, which has a very small area of cross section, high resistance, and the entire EMF battery tends to appear across this entire length of the wire. The next thing you need to identify is that as I've already mentioned, that the area of cross section of the wire is uniform throughout. So if you look at the formula for voltage across the wire, so you say voltage is I times R, and R is rho L upon A. That's a resistivity formula. So for the meter length of the wire, if you see that throughout the length of the wire, the current would be constant. It will have a same constant value of resistivity. It will have, as I said, it has a uniform area of cross section. So I can come to a conclusion that voltage is directly proportional to length. And that's the most important point of this entire concept of potentiometer. So I say that the voltage is proportional to length, hence the entire voltage is divided along the length of the wire proportionately. So if I know the overall EMF, then I can use the ratio formula to get the voltage across any length of the wire. So I can sort of get a formula saying that E upon 100 is equal to V upon L. So which means if I know that the entire 100 centimeter has an EMF E, and if let's say I know the EMF E, so I put that value over here. So for any amount of length, I can get the voltage across it. Let's assume that I give you the value of EMF as 12 volts. So, and I'd say, what's the voltage between 0 and 50 centimeter mark? So you would say 12 upon 100 equals V upon 50. And hence the voltage comes out to be, or let's say, if I'd say, what's the voltage between 0 and 70 centimeter mark? So you would say 12 upon 100 is equal to V upon 70. And hence you can just sort of cross multiply and get yourself the value of the voltage. Which is coming out to be 8.4 volts. Okay, so the other thing that I was trying to explain you about potentiometer is the fact that the major purpose of potentiometer is to measure the EMF of the battery. So we've already done this particular concept saying that if you connect a battery to an external circuit, then it will have different voltages across the battery when you close the switch and when you open the switch. When the switch is open, you'll get a larger value across the battery, and when the switch is closed, you'll get a smaller value. This happens because of the resistance of the battery itself. So when battery is driving current, then a voltage drop appears across the resistance of the battery. And that new voltage is called terminal potential, which is lesser than the actual EMF of the battery. And this happens because of the internal resistance. So when I connect a voltmeter to a battery to measure its EMF, I would not be able to do that. What I end up measuring is the terminal potential. I use a very high resistance voltmeter, but still, as the current flows, there must be some sort of voltage drop across the internal resistance. because of high resistance voltmeter, little current flows, and there would be a little voltage drop across the internal resistance. But there would be a voltage drop, and hence, with the voltmeter, you're unable to measure the EMF. Something that you can measure is always going to be the terminal potential. So, guys, if you that's basically the limitation of it. So we can use this potentiometer to measure the EMF of the battery as well. So you connect two batteries, one with unknown EMF and the other one with the known EMF, and they are connected with a null deflection galvanometer. Null deflection galvanometer has basically it's a sensitive ammeter which shows deflection in both directions. So it just first of all, it's very sensitive in measuring the current. Secondly, it also tells you, because it can deflect from both sides, so it also tells the direction in which the current is flowing. So what you can do is that you can slide the contact of the potentiometer over the length of the wire, and you can search for zero deflection. When I connect this to a zero deflection galvanometer, and when I slide and search for a zero deflection point, so if it's a zero deflection point, so that means there's no current flowing. And when does the current not flow? When there is no potential difference. So that means the voltage between A and B must be equal to the voltage between X and Y, because had there been a difference of potential, then there would be a current flow. So searching for a zero deflection point actually gives me a point where the voltage between X and Y becomes equal to the voltage between A and B. So guys, as I've already told you, I choose one battery with known EMF and the other battery with the unknown EMF, and I find out the zero deflection points for both of them. So if that be the case, E1 over L1 must be equal to E2 over L2. So if I know one EMF, I must be knowing one of the two EMFs. So if I know one EMF and I know the 2 points of zero deflection, so I would be able to measure or calculate the other unknown EMF. That's how I can determine the EMF of the battery. The best thing about this circuit combination is that it gives you EMF and not the terminal potential. That's because since you've found a zero deflection point, so you know there must be no current flowing. And since there's no current flowing, so there would be no potential drop across the internal resistance. So what you measure here is actual EMF of the battery and not the terminal potential.